In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 78. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with polarization forces in a non-uniform electric field. The most common type of transformer oil is based on mineral oil, which is rather constituted mainly with nonpolar hydrocarbon molecules. The electric field distribution in transformer insulation system would have been more uniform during normal steady state operation, whereas there are factors which are being responsible in contributing non-uniform field distribution across different operating conditions. Non-uniform electric fields within transformer insulating fluid are often occurring, particularly during transient operating period such as switching operations or lightning strikes. Transformer is constituted with the distributed inductance, capacitance, and resistance within the complex winding structure. Winding within the transformer that are literally made to form distributed capacitance between turns, coils, and to the ground, that is core and tank. The formation of these capacitance would cause a non-uniform voltage distribution across the windings at the time of transient overvoltages. During transient operation, there would have high frequencies voltage surge associated with steep voltage wavefronts, which thus to create non-uniform voltage distribution across the transformer windings. The transient voltage pulse, while propagates through the winding, can create resonant oscillations as due to the presence of capacitance and inductance in the winding. Resonance phenomenon obviously can cause significant voltage amplifications inside the winding, creating abnormal voltage stresses on the insulation. At the same time, the voltage oscillations would force the voltage to be unevenly distributed along the winding, creating areas of very high stress regions. Underneath effects that are to exhibit within the transformer due to formation of localized high stress regions, that is thermal stress and electrical stress. The occurrence of electrical discharge under a non-uniform electric field within the transformer oil would have to impose substantial amount of electrical stress and create localized thermal stress. The combined effect of these two stresses, that is thermal stress and electric stress, would thus to accelerate the degradation process of the insulating oil and the solid insulation system, which, if sustained, can culminate in catastrophic transformer failure. These two stresses would have been further aggravated by the excessive electric field concentration around the possible contaminants in the oil like gas bubbles, impurities, or suspended particles. It is to note that the electric field concentration or distortion around the contaminant in transformer oil would have to occur because of the difference in dielectric constant, that is permittivity and or electric conductivity between the contaminant and the surrounding oil. When an electric discharge occurs, the field lines that tend to concentrate in the material with having the higher permittivity to minimize the overall energy, leading to a localized decrease in electric stress around the contaminant. Differences in electrical conductivity also play a key role, especially with contaminants like metal particles or carbonized components resulting from degradation of cellulose. It is as because the conductive particles can form localized conductive regions or channels that distort the electric field and would have to facilitate charge transfer, thereby increasing the probability of partial discharge and eventual electrical breakdown. Bubbles, impurities, and suspended particles in the oil, as they create areas of high electric field strength. So, ultimately, that would lead to initiate partial discharges. Effect of thermal and electrical stress as developed due to discharge in a non-uniform electric field. The combined effect of thermal and electrical stress as developed by discharges in a non-uniform electric field that would cause a significant degradation of physical and chemical composition of the transformer oil as well as of the solid insulating components. Thermal stress as generated by the partial discharges in non-uniform electric fields would have to accelerate the degradation of transformer oil much faster than under the normal operating conditions. The combined stress that has to initiate high temperatures and electron bombardment from discharges causing to break down the hydrocarbon molecules in the oil. Such phenomena would lead to instigate in generating active gases like hydrogen, methane, ethane, ozone, nitrogen oxides, and other decay products. Thermal stress causing high temperature and particularly while being combined with oxygen would have to initiate the process of oxidation reaction within the oil. Oil oxidation is a complex chemical process that involves a series of chain reactions, and at higher temperatures, the rate of reaction with oxygen increases exponentially. The oxidation, once started, that would become the beginning of the oil's aging process. In contrast to uniform electric field, it is a defining characteristics of a non-uniform electric field where the electric field strength becomes intensely concentrated in specific areas. Non-uniform electric fields in transformer oil would thus to create localized discharges leading to form thermal energy and electrical stress at the localized zone within the oil. Whenever this localized field strength has to exceed the dielectric strength of a small portion of the oil, there would have a localized breakdown, causing to initiate partial discharge. The intense energy release as caused by partial discharge current that helps to heat up the adjacent layer of the surrounding oil, leading to very high temperature and pressure. This transient heat and pressure that would thus to involve in an immediate vaporization and chemical decomposition, that is pyrolysis of the oil's hydrocarbon molecules, causing to form a combination of low density gases byproducts and gas pockets, that is bubbles, within the transformer oil. In a non-uniform electric field, these gas bubbles would have to experience a dielectrophoretic force, as because these bubbles are a dielectric material, that is the gas immersed in another dielectric medium, oil, with a different permittivity, with having a different permittivity. The dielectrophoretic force on gas bubbles in transformer oil is a non-uniform electric field force that drives the bubbles towards or away from regions of high field strength, depending on the relative permittivity of the gas and the oil. Transformer oil has a relative dielectric constant or permittivity, typically ranging from 2.2 to 2.4, while gas like air has a relative permittivity very close to 1. In accordance with the lower relative permittivity, this dielectrophoretic force drives these gas bubbles away from the region of strongest electric field toward areas of lower field intensity. The magnitude of dielectrophoretic force F is proportional to the bubble's volume V and square of the electric field gradient E. Therefore, dielectrophoretic force F is directly proportional to V into E square. Transformer oil itself is primarily composed of nonpolar hydrocarbon molecules. But the nature of the gas molecules, whether they are polar or nonpolar, that has to depend on the specific cause of gas generation within the transformer. Underneath gases, which are often generated in transformer oil and found as in dissolved state, would have been composed of nonpolar or only very slightly polar molecules. 1. Hydrogen, methane, ethane, and ethylene. Nonpolar molecules have the basic characteristics of an even distribution of electrons, resulting in no positive or negative poles. These gas molecules are therefore being typically nonpolar, as because the electron distribution is balanced, meaning the charges are shared evenly and there are no permanent dipoles. Hence, these nonpolar gas molecules are being configured with zero net dipole moment and causes those molecules to be insoluble in polar solvents like water, but soluble in nonpolar solvents like transformer oil. Polar molecules in transformer oil would have to accumulate over time due to oxidation reaction, which breaks down the nonpolar hydrocarbon chains into polar compounds. High temperature and high moisture in a transformer can lead to the formation of bubbles, water vapor bubbles in the insulating paper, which is highly polar molecules. Stages of degradation at elevated temperatures on cellulose part of the solid insulation. At temperatures between 120 degrees centigrade to 140 degrees centigrade, cellulose intermolecular dehydration reactions begins to activate at temperature 120 degrees centigrade to 140 degrees centigrade, causing to an involvement in removal of hydroxyl groups, OH groups. Such phenomenon leads to a reduction in the number of free hydroxyl groups on the surface of the cellulose molecules. At temperatures above 140 degrees centigrade to 160 degrees centigrade, around this temperature range, cellulose begins to thermally decompose with the slow breakage of glycosidic bonds that would lead to a process of cellulose depolymerization mechanism. Such an occurrence would be the primary cause of the loss of mechanical strength in the paper. At temperature above 160 degrees centigrade to 220 degrees centigrade. In this temperature range, cellulose insulation undergoes severe and rapid degradation primarily through a process called thermokinetic degradation or pyrolysis. Even at the nitrogen cooling system, the 160 degrees centigrade temperature can have to initiate the formation of free radicals within the cellulose structure. At around 220 degrees centigrade, the breakage of hydrogen bonded hydroxyl groups would have been potentially accelerated by the process of thermal oxidation. Involvement of auto-oxidation mechanism would therefore to initiate at the temperature range of 200 degrees centigrade to 220 degrees centigrade, causing to propagate severe thermal decomposition reaction. During this temperature range, there would have to produce various byproducts, including gases like carbon monoxide and carbon dioxide, along with some wooden products which can diffuse into the surrounding insulating oil. Significant glycosidic bond cleavage and depolymerization of the cellulose polymer chain generally begin at temperatures exceeding 300 degrees centigrade. However, the maximum rate of thermal decomposition for cellulose typically occurs within the temperature range of 360 to 400 degrees centigrade. Cellulose, the primary component of the paper insulation, is being constituted with a naturally grown long chain polymer of glucose units. The strength and durability of the paper insulation would have to depend on the structure formed by the long chains of repeating glucose units linked together. The cleavage of glycosidic bonds in cellulose paper insulation would thus to indicate that the paper has lost its structural integrity, causing to degrade its critical electrical and mechanical properties. The ongoing process of this glycosidic bond cleavage is also known as depolymerization, where that has made to shorten the long cellulose polymer chains into smaller fragments. Such happenings would be the primary indicator of the paper's remaining lifespan. It is as because the length of the cellulose chain is measured by its degree of polymerization. Key issues that are to intervene the system of electric field concentration and distribution in a transformer. Non-uniform distribution of electric field throughout the winding configuration of a transformer is inherently exhibited, especially during transient voltage events like lightning strikes or switching operations. Non-uniformity of field distribution is primarily caused by the relative characteristics of the winding's distributed inductance and capacitance, the physical positioning of the components, and the frequency of the applied voltage waveform. The electric field distribution would have been readily influenced by the physical arrangement of turns and coils, including factors like coil height, conductor placement within the slots, and insulation thickness. All these aspects are responsible for basic adjustment of electric flux fringing and magnetic flux fringing. Which would thus to contribute subjective variations in field strength. Magnetic flux fringing in a transformer winding is the most actual phenomenon of magnetic flux lines bulging outward at an air gap, such as a core joint or a winding's edge. Magnetic fringing mechanism that has to occur where magnetic field lines are going to pass through from a high permeability material, the core, to a low permeability medium like air. In core to air transition, it is quite evident that most of the magnetic field lines would always prefer to stay concentrated in the high permeability iron core area of transformer. But at the boundary with a low permeability medium like air, the lines tend to spread outward like a bulge at the edges instead of continuing in a straight line. Even small air gaps within the core or at core joints can cause flux to bulge outward due to the abrupt change in permeability between the iron core and the surrounding air. This is the reason for which air of having a higher reluctance that offers more resistance to flow of magnetic flux, whereas magnetic core with having lower reluctance can easily conduct to the flow of magnetic flux. However, the magnetic flux density in the air gap region as would have to decrease. So, the same amount of flux that has to spread over a larger space area. This has happened because the magnetic field lines always have to repel each other as they pass through the air, which has a lower magnetic permeability than the iron core. Magnetic permeability is a measure that quantifies how easily a material can support the formation of a magnetic field and allow magnetic field lines to pass through it. Because of the high permeability, magnetic field lines prefer to travel through iron core rather than air gap. Magnetic field lines within the iron core do not repel one another. Rather, they are bunched together along the path of least magnetic reluctance. This causes the flux to become densely concentrated, resulting in a significantly stronger magnetic field in the iron core compared to the surrounding air. Magnetic fringing effect would therefore more significant with a larger air gap, which in turn lowers the effective magnetic flux density in the air gap region. It is quite evident that the magnetic flux leakage and magnetic flux fringing both are often described as undesirable physical phenomena with having different causes and implications while in an ideal ferromagnetic induction system. Adverse effect of magnetic flux leakages in power transformers. Magnetic flux fringing is a localized effect occurring at the air gap that contributes to leakage flux, whereas leakage flux itself is a broader phenomenon that can appear in various regions of the magnetic circuit, including around the windings. Therefore, magnetic flux fringing that has to occur specifically at the edges of the air gap, not throughout the entire magnetic circuit. Magnetic leakage flux in power transformers is the portion of the flux that does not follow the intended high permeability core path and often completing its path through low permeability surroundings such as air or nearby structural parts within the transformer. Such occurrence is rather to be a consequence of imperfect magnetic circuits where a portion of the flux escapes, creating a magnetic field in the space around the winding. As this leakage flux can have to link with either the HV and LV winding, but not both, so it does not participate in transferring power from one circuit to the other. The leakage flux, which does not link both the HV and LV windings, would then involve in introducing self reactance in each winding, effectively behaving as a series impedance with the winding. Hence, higher be the leakage flux, that leads to greater leakage reactance. However, there are several reasons for which leakage reactance in a power transformer would have become significantly high, causing a voltage drop under load. Such an effect leads to poorer voltage regulation and a reduction in overall transformer efficiency. Higher leakage reactance in power transformer is primarily caused by the underneath factors. One, a larger physical separation between HV and LV windings would obviously have to create an increased leakage flux path. With a larger interwinding gap, a greater portion of the magnetic flux tends to travel through the air between the windings rather than linking both windings, thereby increasing the leakage flux. Number 3, therefore, a compact or relatively smaller interwinding gap that reduces leakage flux and enhances mutual flux linkages, resulting in lower leakage inductance and higher interwinding capacitance. The shape and arrangement of windings such as cylindrical or disc types would have directly influenced the distribution of leakage flux because a greater winding height or larger diameter increases the available path for leakage flux. To minimize the physical spacing between HV and LV windings, transformers are preferably designed with compact sandwich or interleaved winding configurations. In sandwich or interleaved winding configurations where the HV and LV windings are divided into multiple sections and being alternately layered. Each corresponding segment of the HV and LV windings is designed to carry an equal number of ampere turns, thereby ensuring proper balancing of the magnetomotive forces across the adjacent sections. The degree of leakage flux in a transformer can significantly be controlled by subdividing the HV and LV windings and interleaving those windings. This technique has made to bring the high and low potential windings into closer physical proximity. Number 10, thereby allows a greater portion of the magnetic flux to traverse the interwinding gap and link both windings rather than dispersing outward as leakage flux. 11. However, a higher degree of subdivision results in correspondingly lower leakage reactance. Therefore, such winding configuration has effectively met to improve the magnetic coupling, keeping the magnetic leakage flux low and thereby reduce the overall leakage reactance. Among the several variants of transformer windings that have been developed and progressively refined over the decades, the interleaved winding stands out as a significant breakthrough. As a matter of fact, transformer equipped with windings of interleaved turn would have the most effective alternative to continuous disc and layer windings for a wide range of transformer output and voltage ratings. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also, share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.